I'm Orr Roberts, and I'm going to show you some film clips that illustrate some of the work of the National Center for Atmospheric Research here in Boulder, Colorado. These first scenes show the sun. They're time-lapse photographs showing the gigantic eruptions called solar prominences that shoot out from the edge of the sun. The bright face of the sun is eclipsed by a very complicated telescope called a solar coronagraph. I took many of these back in the early 1940s. In this next scene, for example, the largest solar prominence ever observed by man. It shot out at a speed of about 1,000,000 miles an hour. The distance from the edge of that black disk to the top of the frame is about 200,000 miles. So you see that huge eruption went out very, very fast. This scene shows a very striking, large field of activity. Notice how those white knots of solar prominence material rain down along curved trajectories. Those trajectories, we now know, define the magnetic field of the edge of the sun in which these solar prominences are governed. These things are all terribly interesting to us in understanding the effects of sun on Earth. The next scene now is a scene showing a layer of smog as photographed from the roof of our NCAR laboratory looking down towards the city of Boulder. You can see in the center of the photograph, near the ground, clouds of smog sloshing back and forth like water in the bottom of a bowl. And if you look up at the top, you can see clouds moving along at rather high speed. Remember that these are time-lapse photographs like the solar pictures I just showed, and these too are speeded up about 300 times. There is a very strong temperature inversion or layer of cold air down near the ground, and that cold air acts almost like a body of water in the bottom of a basin, except that here the cold air is filled with smog, which gradually builds up as the day passes. And it's because of the existence of inversions like this that air pollution grows very, very severe. This now is another inversion, but a little bit higher, and this one has a striking feature that it's illuminated by a layer of fog. So you can see the cold air outlined by the fog. And watch that big wave, for example. It goes rolling along. That is a wave on the cold air that is held close to the ground by the density of the cold air in what is called a temperature inversion. The layer above this fog layer is warmer and therefore lighter. So you're seeing a phenomenon very analogous to ocean waves, and they're called gravity waves, very similar to gravity waves in the ocean. Note in the center of the photograph a plume. Look at that huge wave, and there in the center is a plume of smoke from a factory. That heated smoke goes busting up through the temperature inversion and into the air above. And you see it sometimes outlines the motion of the wave that is carried along on the fog layer. I like these photographs not only for their scientific importance, but also because they're enormously beautiful things. And I get quite a thrill every time I see that huge wave roll up onto the mesa. This next scene now is looking north from our laboratory. The clouds are moving from west to east. And notice how clear the mountains are in the background. The temperature inversion here is just a little bit higher than the camera, and it's now bringing in some clouds from the right. The air in the temperature inversion is moving to the left or to the west, opposite to the air above the temperature inversion that is moving to the right. And it's obvious that there's a very striking turbulent boundary between these two contrary moving clouds or streams of air. The clouds that are moving to the left, of course, are in the colder air near the ground, and now you see how the dust and smoke of the air in the temperature inversion begins to obscure the mountains behind. The reason we're so interested in these photographs is that they tell us something about the so-called boundary layer, the layer between the phenomena that occur right near the Earth and the air a little bit higher. This boundary layer is tremendously important in atmospheric sciences. it is the focus where the interactions between the surface of the ground and the atmosphere take place. And these interactions affect the course of jet streams all over the Earth. Notice here how the buoyant clouds from below poke up into the air above, where it's drier and warmer, and then get their tops knocked off and their moisture evaporated. This interaction is of tremendously great importance to us in understanding the processes of the atmosphere. And of course, these cloud photographs, speeded up 300 times as they are enormously beautiful things to watch. We have a tremendous amount of work on this boundary layer activity going on here at NCAR, and it's one of our most important research tools. Now I'm going to show some photographs that show man's impact on the atmosphere. Those sudden streaks that you see, there's one, there's another, shooting along, are jet airplanes flying by, leaving a trail that we call a contrail behind, a trail of ice crystals. Note how the ice crystal trail grows and extends with the passage of time. And as that cloud grows, it encompasses much more moisture, much more ice than was actually spewed out by the plane itself. We're interested in how these clouds, formed in part by man, change the atmosphere. And now I'm going to show a photograph of the genesis of weather systems. This is done entirely synthetically in a gigantic computer. You're seeing at the top a weather map, a pressure map, and at the bottom a temperature map. And on day 0 in this sequence, the atmosphere was completely at rest everywhere at the freezing temperature. Then suddenly we turned on the sun and allowed it to shine down upon the Earth, and we caused the Earth to rotate, all of course in mathematical simulation in our huge computer here at the National Center for Atmospheric Research. In the computer were mathematical models that gave the location of the land masses, the temperature of the oceans, but above all, contained the very complicated equations that govern the motion of the atmosphere. These photographs are photographs of the output of the computer's calculation, making billions of calculations to do these synthetic weather maps. Now, the striking thing is that the weather map above or the temperature map below, now at simulated time 25 days, those maps don't look very much like real weather maps. Notice that pressure center off the east coast of the United States, up over Nova Scotia. It isn't moving. In real weather, those low and high pressure cells move. But watch what happens right now about at day 35. The temperatures in the equator have built up a great deal, as shown by the many, many lines. And the model is unable to accommodate the addition of more heat in the equator without suddenly breaking into a much more complicated regime of flow. And lo and behold, the high and low pressure centers that were previously static begin to move along across the oceans and over the continents. Thus, we have seen something akin to real weather systems born in the computer from a static atmosphere. And it's very exciting to us that by this kind of mathematical simulation, we can come to something so realistically similar to the weather maps that are generated by nature and the real Earth. Now, the models that Dr. Washington and Dr. Kasahara and others at our laboratory have worked out are still enormously simplified. We need to go much farther in the capacity of the computers to make the calculations, the fantastic number of calculations necessary. And we need to make our models more sophisticated. This next scene, for example, shows a model in a little different kind of projection that has clouds in it. The previous one didn't have any clouds or any rainfall, but where you see the white patches here, there are clouds. And the fascinating thing is that each time we add features to the mathematical model that make it more like the real Earth, the weather that the model produces is more realistic to real weather. And we believe that with the passage of 5 or 10 years and the development of the Global Atmospheric Research Program in the late 70s, we will have tools of mathematical simulation that will allow us a realistic estimate of the actual future course of weather, predictions, if you will, and this is the principal objective. I want now to go out in space and look down at the Earth and show some of the kinds of tools that we're using in the atmospheric sciences. This is a beautiful sequence taken from a space camera designed by Werner Sumi at the University of Wisconsin. You're now looking at the Earth. Now it's noon, and notice how the shadow comes and afternoon comes. Now it's late afternoon, and now it has become dark. We're now going to show this speeded up. This is the same day over and over again so that you can see the motion of the clouds. In the center of the photograph is South America. In the upper right, Africa. And notice that gigantic cyclone, that pinwheel in the upper right, that pinwheel of motion of clouds. And notice in the upper center how there's a great jet stream, a streak going from the left, lower left to the upper right of the upper part of the picture. That's a great jet stream extending out across the Atlantic. And the weather map that can be generated from this is quite remarkably useful. We're now zooming down on the Amazon River Basin, and you can notice as you see the same day over and over again how, for example now, late afternoon, you see that thunderstorm build up off the coast there. It's enormously exciting to us that we can derive wind motions from study of these clouds and add to our understanding of what the weather is doing from day to day. But to me, perhaps the most exciting photographs of all are these of hurricanes. These films, by the way, were put together by Ted Fujita at the University of Chicago, and you see here the giant pinwheel of a hurricane, about 4 or 5 hours of the hurricane's life, repeated over and over again, so that you can see the pinwheel character of this incredible, huge tropical storm. Notice in this, the final sequence, how you can see the clouds spinning clockwise, the thin filmy clouds from the top of the hurricane, and then the clouds down at the bottom going counterclockwise into the vortex of the hurricane. These photographs are not only beautiful, showing us something of the power of terrestrial phenomena, but they are also enormously useful scientific tools, and from this will come new understanding about our Earth. Thank you very much.